So for this part of class, we're looking at when is momentum conserved, where you can use like the conservation momentum method, versus when is momentum not conserved? When do you have to use impulse momentum theorem? And it's actually, it's relatively easy to tell apart. When you want to use impulse momentum theorem, this is when momentum is not conserved. Impulse momentum theorem says that you will have some sort of external force which applies an impulse, right? Impulse is force times time. So something is applying an external force for some period of time. That causes the momentum to change. The mass might stay the same, but the velocity of your object changes. So then you have a change in momentum. With impulse momentum theorem, momentum is not conserved because the momentum has changed. The changing momentum means that it's not staying the same. Momentum is not conserved for impulse momentum theorem. And usually what happens, the reason that it's not conserved is impulse momentum theorem only deals with one object at a time. So let me give you an example of that. This might be something like, oh, when you're playing tennis, right? I think we did a tennis ball example. I'm going to make it tennis, but easy to work with numbers. Let's say I just deal with a ball. And initially the ball's traveling towards you. Let's make it 2 kilograms of mass going 10 meters per second. But it's 10 meters per second to the left, which means what? Negative, cool. So its initial momentum is mass times velocity. So that's 2 times negative 10. Its initial momentum is negative 20. Now, since the racket is not part of the system, since you're only thinking about the ball gets hit back and changes direction. Let's say you like put some force behind it. So they hit the ball towards you at negative 10 and you hit the ball back towards them at positive 15. Right? You add a little extra to it. Now it's going faster. Not only does the momentum get larger in magnitude, but it's also changed direction. The final momentum has gone from 2 times 15, so now it's positive 30. If you're looking at this, it looks like a conservation of momentum problem, except it just has one object, and that object has gained momentum, so momentum is not conserved. So how I picture impulse momentum theorem is I do a before and after diagram. That's this picture right here. It's got the mass and velocity of each object, but I also like to picture it with a momentum bar chart, something that shows the momentum has changed. So with a momentum bar chart, this object had negative 20 Newton seconds of momentum to start. And afterwards you hit it and has gone to positive 30. Since the momentum has changed, it's not conserved. An impulse is the change in momentum. So this impulse would be positive 50. It has gained momentum. It goes up 20 to get to 0, and then you apply 30 more to make it change direction. So how I get impulse is I do PS minus PI, final minus initial, so that's 30 minus negative 20. And the impulse has gone up by 50 Newton seconds. So that's an impulse momentum problem. The way you can tell it apart from a conservation problem is you only got one object in your picture at a time. You're only dealing with like the mass times velocity of each object, right? Oh, okay. Conservation of momentum is going to look super similar. In a conservation of momentum problem, now you have 2 objects that make a closed system. The trick with this is the total momentum of both objects stays the same. Since there's 2 objects, one could lose momentum, but the other would just gain that momentum back. And since the other one gains the momentum back, the the total amount stays constant. So let's say I do this with, let's say I do this with a inelastic collision. Let's say I have a train cart hits another train cart, right? Let's say a train cart or like a roller coaster cart pulls into the roller coaster station, and it has like it has a problem, right? Its brakes don't work. So it's traveling at 10 meters per second. And it hits the other roller coaster cart that's full of people, right? And they're gonna stick together. So I'm still doing a before and after diagram. It's now I have two objects. I've got my two different carts. They stick together to make 300 kilograms total, and they move with an unknown speed, VF. I can tell this is a conservation momentum problem because I have two objects, they interact with just each other. And since they interact with just each other, then the total amount of momentum stays the same. What I do is I calculate the momentum for each object. So I'm still calculating the momentum, but now I have to do it multiple times for multiple objects. So the initial momentum of the 100 kilogram roller coaster cart is 1,000. The initial momentum of the 200 kilogram roller coaster cart is 0 because it's at rest. No momentum because it's not moving. Finally, that 1,000 Newton seconds of momentum is going to hit this 300 total massed cart, right? And I don't know the final velocity, so I'm just going to call it VF. So all I'm solving then is 1,000, that's the momentum before, equals 300 VF, that's the momentum after. So last step, divide by 300 on both sides. This gets me a final velocity of like 3 meters per second, 3 and change. So if I look at representations, I still did a before and after. I still took the momentum of each picture. I just had to take it more times because there's more objects. Then I can use conservation of momentum, this statement right here. I can use conservation of momentum because they're only interacting with each other. Now, I can still use the bar chart picture. But if I use the bar chart picture, I need to treat both objects separately. So how this works. Let's say I take the 100 kilogram object, right? And it's going to have a before and after momentum. Its initial momentum was 1,000, right? But because of the collision, it lost momentum. Because of the collision, its new momentum at the end would be 100 times 3.3. So this thing lost momentum. It would only have 333 Newton seconds of momentum. The 100 kilogram cart loses momentum. It loses something like, what is that, 670 something? 667. It loses momentum, so it has a negative impulse. And if you had to guess, that means the other object, right, the 200 kilogram object has to gain momentum. Its momentum before was 0. And now it's a 200 kilogram mass moving at 3.3 meters per second. So it has gained momentum. Momentum is conserved because whichever lost momentum is picked up by the other object. So to sum it up, you can tell these two types of problems apart because in an impulse momentum problem, you're only going to deal with one object at a time. It can't have conservation of momentum because some sort of force causes it to change its momentum. Whereas in a conservation of momentum problem, you have two objects and they just transfer momentum to each other. So the total stays the same. So I'm gonna go have us try a thing right now.